Today we're going to talk about properties of logarithms, and I call it part one because we're just going to focus on one concept. But the what we're going to work with regard to logarithms today is we're going to be condensing them down into one logarithm or less, is what we're going to do. But we need to familiarize ourselves with these properties that we're going to be using really, I think, for the remainder of our unit here. And in fact, I'm going to start with the last property because it's the one that we always need to look for first. It's the power property of logarithms. If you took Algebra 2 last year, we spent an inordinate amount of time on this concept. And all that the power property says is if we have log base b of m to the p, so we have an exponent on our m there, what happens is that that exponent becomes a coefficient of the logarithm. We can move the p from the exponent position out in front of the logarithm. And again, as we work through our examples here in a few minutes, that's the one that we always want to look for first. Do we have a coefficient when we're working with these? The other properties here, the first one, the equality property of logarithm, says if log base b of m equals log base b of n, then m equals n. And essentially what that's saying is we've got like bases. This is log base b on the left side, and we have log base b on the right side. That's the part that's already the same. So what we need to do to solve is we need to take what's sometimes called on the internet the argument of m and set it equal to the argument of n and solve there. In other words, the bases are the same. We could cross them out and solve what we have left. But the bases are the same. Then the final two here, product property. Remember that the definition of logarithm, or at least what I oftentimes refer to logarithm as, is it's another way of writing an exponent. So the product property links back to this fact that a to the m times a to the n, what do we do to the exponents when we multiply those two? We add them. And the same thing happens here. Log base b of m plus log base b of n. Well, if we want to turn it back into a single logarithm, we have the same bases already. All that we need to do is we need to multiply the m with the n. And it comes from that a to the m times a to the n equals a to the m plus n. Same kind of logic on the quotient property of logarithms. I'm specifically looking at the right side of the equation and turning it back into the left because we want to turn our problems that we're getting close to working back into one logarithm or less. And this one goes back to the quotient. So if we're dividing like bases with exponents, what we do is we subtract and we get a to the m minus n. And look what happens here. Log base b of m minus log base b of n converts into, when we condense it down, back into dividing. And some of that might not make any sense at all, but I hope as we go through our examples here that I can make some sense out of them. Unfortunately, these properties may be something that you need to memorize. At the very least, we need to familiarize ourselves with them. But let's see if we can apply them. And the nice part for you is that you can see that table on your paper as we look at these examples. The first one being we're going to write each of the following as a single logarithm, express all powers as factors. Well, like I said a few minutes ago, look and see. Do we have a coefficient, a number in front of log base 4 on either of the log base 4s? And in this particular problem, we do not. So the second thing that we look at is we see that we have a subtraction sign. Well, the property that has subtraction in it is the quotient property, which is the third one there in your table. And what we can do is we can convert this problem back to division now. The minus means that we can rewrite this as 32 divided by 2. So we've condensed it into one logarithm, which is our goal. The question now is, can we simplify it any further? And I bet that a few of you recognize that 32 divided by 2 is 16. And the question now is, can we simplify this any further? And if you notice, we've got two parts of a logarithm. We know log base 4 of 16. And since we know two pieces, we can figure out what this value equals by converting it to an exponential. And our exponential is going to be 4 to the p equals 16. Well, 4 to what power equals 16? And it's 2. And in this case here, our answer, so log base 4 of 32 minus log base 4 of 2 is 2. And what we're trying to do today, again, is we're trying to condense it down into one logarithm or less. So we converted it to one logarithm, but we were able to simplify that logarithm and actually find a value in this case. Let's try another one. Again, power property of logarithms. That's the one we want to look for first. What we see on this particular problem here is that we do have a number out in front of the logarithm. We have a coefficient, and we have a coefficient actually on each of those values. And what we can do is when we have a coefficient, we can take that coefficient and instead write it as an exponent. So we're going to be able to write both of these, the 6 and the 5, as exponents. So our first step here, log base 2 of x to the 6th, the coefficient became an exponent, plus log base 2 of y to the 5th. And our goal, we want to write this as a single logarithm. Well, what does plus tell us to do? You can look at the top of your paper there, and what you see with regard to the addition here is it's the second one. It's the product property of logarithms. When we have addition in our logarithm, we can condense it down by multiplying our m and our n in this case, or on our actual example here, we can multiply our x to the 6th and our y to the 5th together. We cannot simplify anymore. One thing, I think oftentimes you'll see parentheses around it just to make sure that the log base 2 applies to that entire value. But I didn't write that on my paper. But as I'm standing up here, I think we need to. So number 3, we've gone from fairly short problems all of a sudden to this one. But if you look at it, log base 4 of 5 plus log base 4 of x plus log base 4 of 4 plus log base 4 of x minus log base 4 of 2. First thing to notice is that they're all log base 4, and that's important, like bases. But when I look at this problem, what I'm going to recommend is we do all of that part together because all of those terms are added together. And so when we see multiple addition signs in this problem, the property that has the addition sign in it is the product property. So even though we have multiple addition signs in here, what we're going to do is we're going to take log base 4 of 5 times x times 4 times x. But don't forget, we haven't touched the minus yet. But we're able to condense down a lot by using that product property. And in fact, we can even simplify what's in that parentheses a little bit more. We get log base 4 of 20x squared minus log base 4 of 2. But our goal is to write this as a single logarithm. So to write this as a single logarithm now, we've got a minus. We look back at our chart, and which one of these deals with minus? Well, the third value here, the quotient property. So we've got log base b of m minus log base b of n. We can condense that down into log base 4 of 20x squared divided by 2. And then the question remains here, can we simplify that anymore? We've got a single logarithm now, but can we do any simplifying? And 20 divided by 2 is 10. But we can't do any more than that. We've got a variable in there, and in fact, if we set it equal to p, we'd have 2 variables. We need to know 2 parts of a logarithm out of the 3. Number 4. And I didn't do it on that last problem, and I don't know why, but we should always look and see, do we have a coefficient on the logarithm? We have 1. We have this 2 here. So this is going back to the power property of logarithms. And what we're going to do is we're going to rewrite this 2 as a power. So we're going to take this and we're going to make it an exponent on 6. Don't forget, we have like bases. So it's going to be log base 4 of 6 squared minus log base 4 of 9. By the way, some of you said, I'm not going to write 6 squared. What's 6 squared equal? Well, it equals 36. So you may have skipped that first step there and just gone to 36, and that's fine. What do we have to do now when we see a minus sign? I'm going to divide. Going back to that quotient property, look for the minus property. It's the third one. And we get log base 4 of 36 divided by 9. Again, some of you are going, well, I'm not going to write down 36 divided by 9, because what does 36 divided by 9 equal? It equals 4. So log base 4 of 4. Once again, in this particular problem, now we've got it as a single logarithm, but we know the base, and we know a number. What we want to find is, what's the exponent here? We can actually figure out this value. Remember, a logarithm is another way of writing an exponent. So this is 4 to the p equals 4. And 4 to what power equals 4? 1. So when we simplify that, we actually get a number. We get a single logarithm or less. We get less. Number 5. Log base a of 7 plus 4 log base a of 3. Do we have any coefficients? We've got a coefficient. We need to deal with it. We've got this 4. This is going to be log base a of 7. The coefficient is going to become the exponent on the 3, which is log base a of 3 to the 4th. And again, some of you might not even write down 3 to the 4th, You might write down the fact that 3 to the 4th is 81. Well, what operation does plus tell us to do? And hopefully you're thinking multiply. So log base A of 7 times 81. Well, 7 times 81. Log base A, 7 times 1 is 7, 7 times 8 is 56. So log base A of 567. We have it in a single logarithm, then we need to ask ourselves, can we simplify any more? But we only know one number. It's log base A. If we had some value there for the A, we might be able to figure it out. But we don't. We only know one part, and there's 3 parts to a logarithm. Number 6. 2/3 is the coefficient. Goes back to our power property. So when we've got that 2/3 here, we're going to make that an exponent on the 8. Now in this particular problem, this is a natural log, but the same properties occur whether we're working with log or we're working with ln. So natural log here of 8 to the 2/3. And let's simplify a little bit here. We just solved 3 to the 4th in our last problem. It was 81. So we can simplify a little bit there. Well, then the next question becomes, do you remember how to figure out what 8 to the 2/3 equals? And as a refresher here, remember that the base becomes the radicand, the number underneath the radical. The denominator is the index. It goes in the check mark part of the radical. And then we can finish by squaring it. Well, the cubed root of 8, do you know what the cubed root of 8 is? It's 2. And then we square it. So what we have here is we have the natural log of 4 when we simplify that. Over here for our term to the right, this is going to be the natural log, and 81 minus 8 is 73. What operation does minus in a logarithmic expression tell us to do? We're going to use the quotient, and quotient says that we divide. So we can finish now by putting this into a single logarithm, and it's going to be 4 divided by 73. The first one divided by the second one. Number 7. Log base A of x plus log base A of 9 plus log base A of x squared plus 1 minus log base A of 5. It kind of goes back to what we did on example number 3. When we look at this here, I like to do all of this part first, all of that part that I just underlined first, because it's log base A of x plus log base A of 9 plus log base A of x squared plus 1. And when we see the plus, that's telling us to use the product property, and the product property says that we're going to multiply x times 9 times x squared plus 1. And we still have our log base A of 5. We can simplify this down a little bit, and we get log base A of 9x times x squared plus 1 minus the log base A of 5. And we could even distribute that 9x if we wanted to. It's not going to make that much difference here. But we get log base A of 9x cubed plus 9x minus log base A of 5. But we dealt with the pluses, the addition symbols in this problem. With our product property, we have a minus now that we need to deal with. And that's going to be our quotient property again. And our quotient property says that we can condense this by saying log base A of 9x cubed plus 9x divided by 5. Number 8. We don't have any coefficients in this one, nor did we on our last problem here. But this one says log of the square root of x. And what happens here is we can rewrite the square root of x as log of x to the 1/2. We can use a fraction exponent, which is going to help us simplify this problem. And just a reminder here that there's no number in the checkmark part of the radical, so it's a 2. It's understood 2. There's no exponent on the x, which is an understood 1. And the number in the checkmark part is what's going to go in the denominator. It's x to the 1/2. Over here, minus log of x to the 6th. And once again, what our goal is to condense, to make this, to rewrite this so that we only have one logarithm or less in the problem. Well, we have a minus sign. Minus says that we can condense here by division. We've seen it in the last few problems. And we have x to the 1/2 divided by x to the 6th. But once we get it written in this format, we can do something else to the problem. Remember when we divide, because we have x to the 1/2 and x to the 6th, we actually can divide those values, and it becomes log of x to the 1/2 minus 6. If you need to, you can type that into the calculator, and we have 1/2 minus 6, and it might be nice if I pressed equals here. Gives us negative 11/2. So we can't do anything to the x, but we've got log of x to the negative 11/2. And to finish, we're going to use the power property here. And what the power property says is we can take this value and we can write it as a coefficient. If you look back at the directions, it does say that we want to express all powers as factors. So negative 11/2 times log of x.